Current projections estimate that by the year 2030, artificial intelligence will contribute up to $13 trillion to the global economy. The sheer scale of this technological boom makes it feel like an overnight revolution. But the core concepts driving these modern algorithms are actually of retirement age. To understand the actual trajectory of our future, we have to examine exactly why this specific technology crashed, burned, and almost died twice. In the summer of 1956, a group of scientists gathered at Dartmouth College to study computational intelligence. They were working with room-sized hardware that possessed severe memory and speed limitations, but this meeting marked the formal birth of the artificial intelligence field. The project was driven by a highly optimistic conjecture from mathematician John McCarthy. He proposed that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. This conjecture led to the creation of symbolic AI. Symbolic AI was an early approach where programmers attempted to manually hard-code the strict rules of human logic, line by line, into a machine. The initial results were highly convincing. A program called the Logic Theorist successfully proved mathematical theorems, and a chatbot named Eliza simulated a psychotherapist well enough to keep users talking for hours. The press published highly optimistic predictions, and the defense sector poured millions of dollars into further research. But the architectural approach was fatally flawed. Attempting to manually write rigid rules for the entirety of human thought proved impossible to execute against the strict processing limits of 20th century computing hardware. The collapse of that early optimism triggered the first AI winter. An AI winter is a multi-decade period, most notably in the 1970s and 1980s, where research funding completely vanished and artificial intelligence became a disgraced term within computer science. A major catalyst for this collapse was a 1969 book by Marvin Minsky and Seymour Papert. They published mathematical proofs detailing the severe limitations of single-layer perceptrons. A single-layer perceptron is a simple early neural network that passes data through only one layer of input and output nodes, making it completely incapable of solving complex, nonlinear problems. Once those theoretical limits were exposed in print, government agencies like DARPA lost patience. They slashed academic funding and abandoned high-profile defense projects, including early attempts at machine translation and autonomous tanks. The industry collapsed because the foundational concept of rigid, single-layer logic was a scientific dead end. To survive, researchers had to abandon strict mathematical rules and expand outward into multi-layer neural networks. A neural network is a machine learning model designed to mimic the overlapping, interconnected structure of the human brain by processing data through multiple hidden layers of artificial neurons. The critical mechanical breakthrough arrived in 1986 with the rediscovery of backpropagation. Backpropagation is a mathematical method that allows these multi-layer networks to measure their own prediction errors and then automatically adjust the internal connection weights between their nodes to correct those errors. By utilizing backpropagation, engineers no longer had to manually write the rules of logic. This changed the nature of computers from rigid rule followers into systems capable of teaching themselves through repetitive trial and error. Those 1980s algorithms sat largely dormant until the 2010s. That is when the theoretical math finally intersected with the invention of massive GPU processing power and the sudden explosion of global big data. The combination of better hardware and learning algorithms produced a rapid succession of victories. In 1997, IBM's Deep Blue defeated world chess champion Garry Kasparov by calculating 200 million positions per second, demonstrating the triumph of raw computational scale. In 2011, IBM's Watson defeated two human champions on the game show Jeopardy! This required the machine to successfully process the extreme nuance, puns, and ambiguity of natural human language in under 3 seconds. Then in 2016, DeepMind's AlphaGo defeated world champion Lee Sedol at the ancient game of Go. Because the game has more possible board positions than atoms in the universe, the machine could not rely on pure calculation. It had to develop distinct, creative machine intuition. The original multi-layer architecture from 30 years prior was correct. The field simply had to wait for feasible hardware to catch up to the math. Despite these high-profile victories and the current financial boom, all existing models are still classified as narrow AI. Narrow AI refers to systems that are strictly confined to highly specialized single-domain tasks, like playing a board game or generating text. The ultimate unrealized goal of the field is artificial general intelligence, or AGI. AGI is defined as a system fully capable of the entire spectrum of human problem-solving. Reaching that general threshold remains the field's greatest challenge. Many researchers argue that just adding more data to current models won't be enough, that true general intelligence will depend on technical inventions we haven't seen yet. This chart plots data from a survey of industry experts conducted by researchers Vincent Mueller and Nick Bostrom. It shows the median expert prediction assigns a 50% probability that high-level machine intelligence will be developed between the years 2040 and 2050. The survey also tracks what happens after that threshold is crossed. The experts predict that within 30 years of achieving general intelligence, the systems will rapidly evolve into a superintelligence. Superintelligence is defined as an intellect that greatly exceeds the cognitive performance of humans in virtually all domains of interest. The same researchers found that experts estimate a 1 in 3 chance that this development yields extremely bad consequences for humanity. The final challenge is not figuring out how to build a mechanical mind, but ensuring we can survive our coexistence with it.